So going aboard. Your learning journey starts now. Ever wondered if there's an endless stream of prime pairs just two apart? Like 3 and 5 or 11 and 13? That's the twin prime conjecture. We know gaps between primes get small infinitely often, but is that gap always exactly 2? Mesh 8.0 throws a curveball. We can't even use the words prime or gap 2 until we build something solid. Suspenseful, right? So, how do we build this without cheating? Enter the 5-core secret sauce. Think of it like a recipe for twin primes. D says everyone uses the same basic template. I insist the new dish is different from the old ones, no relabeling. Demands everything is complete, basis, gap, context, the whole shebang. Is picky. Only the gap of 2 will do, and both numbers must be prime basis, and P. It's the engine. Take any finite collection of known twin pairs, and it spits out a brand new one beyond its boundary. Each core has its job ensuring rigor. Now let's see this machine run. It follows a specific path. P kicks off, generates a new candidate using D's template. I ensures it's genuinely new. K checks if both parts are complete primes. W locks in the gap of 2, and P wraps it up, ready to start again. You take any finite list of twin primes, say up to 1 million. Our system finds a new pair bigger than 1 million. Register it. Now you have a slightly larger finite list. But guess what? The process can repeat. There's no end in sight because the ability to generate more is never exhausted by any finite list. Infinitude isn't about listing forever. It's about this open regeneration loop. Okay, this is cool internally, but how does it connect to the classic math problem? Through a fidelity compiler, phi. Think of it as a translator. We need 5 promises, f1 through f5, to make sure our semantic objects map perfectly to classical integers. f1, our semantic base, is a real prime number. Our gap of 2 means q minus p equals 2. f3, completion means both p and p2 are prime. f4, being beyond the boundary means p is greater than any given b. f5, each new package is a genuinely new integer pair. If all these hold, then our internal proof directly implies the classical twin prime conjecture. For any bound b, there's a prime p bigger than b such that p plus 2 is also prime. Q almost. So why go through all this semantic gymnastics? Because it avoids circular logic. We don't assume primes exist first. We define the structure and primes emerge from it. A finite list of examples doesn't kill the possibility of more. It's a proof focused on relationships and generation, not just counting numbers. The F1 to F5 contracts lay the groundwork for bridging to classical number theory. The big takeaway? Twin primes aren't just scattered numbers. They're manifestations of a deeper repeating semantic pattern. Pretty neat, huh?